What is up, YouTube? Welcome back to another episode on Code with Annie. In this episode, I'm going to show you one of the most commonly asked problems with respect to sorting, which is a very simple problem, but it might look complex when it is given to you, but it can be solved very quickly with the help of quicksort. It is nothing but the sorting of a binary array in a single pass. What I mean by single pass is, in one go, you need to sort the entire array. So by the time you start from the first to the last element, the array should be sorted is what they mean. But this can be achieved by using the quicksort technique, wherein just pick up the pivot element and all the elements less than pivot will be on the left side of the pivot, and all elements greater than the pivot will be on the right side. So in a binary array, the elements that you see is only going to be 1 and 0, right? So let's say something like this is the array, right? Now, if you pick up the pivot element as 1, which is the first element here, all the elements less than or equal to 1 or less than 1 should fall on the left side of 1. So zeros will go to the left of 1 and all the ones will be on the right side of 1, right? So by the time you're done with one single pass of this quicksort for this particular array, you will already have the array sorted, because at the end of this, you will end up having this array here, 0, 0, 0 and 0. Then there are 5 ones, right? Yeah, so this will be the end result of your sorting. So this question, whenever is asked to you, you can say that you can simply use a quicksort algorithm, because in the quicksort, once you pick up a pivot element, all the elements less than the pivot will be on the left of pivot, all the elements greater than pivot on the right side of the pivot. So when you're done with it, you will already have the elements sorted, because there are only 2 elements under consideration in a binary array. I can show this in the code as well. If I have this, I have put this already here. So I've already sorted it once and seen. So this is the array, for example, I've taken. Let me run this once again for you, and here we go. So this will run very fast because the sorting is only a single pass sorting. So by the time I reach the point wherein I have the partition index, we would already have the sorted array, which is, because this is a binary array and just 2 elements are in it, it's going to be sorted in a single pass. So this is what they mean, and this is what they mostly expect when they ask you this particular question in your interviews. Okay, so keep this in mind, and if you like this video, do hit the like button, subscribe to Code with Annie if you haven't already, and keep sharing these videos. And oh, one more thing I forgot to mention: the quicksort's time complexity on average case is going to be O of n log n. The reason it's n log n is because quicksort follows something called as a divide and conquer strategy. What do you mean by divide and conquer is, basically you divide this array into logical subarrays, right? So when you pick up a partition index, when you pick up a partition element or a pivot element, you divide the subarray logically into 2 halves, one with less than or equal to the partition element and one greater than the partition element, right? So since you do this kind of a division, it basically looks like a tree if you look at it. For example, let's say the array is something like this one, okay, 2, 4, 5, for example. This is logically partitioned into 0, 1 will be sorted if you're picking up 2 as pivot, and then you have 4, 5, and then this further gets sorted into 0, 1. This sorting happens between these two, then sorting happens between these two, just for the sake of example I've given. So if you look at this hierarchy of breaking down these elements, right, as you go down, you just keep on creating subarrays, and then you have the completely sorted array once you have sorted all the individual subarrays. So this kind of a technique is called as a divide and conquer technique, and the same technique is usually applied in case of merge sort as well, which is the next algorithm we'll be taking a look at. And whenever you have such kind of a division of the array and it goes on dividing into subarrays, your time complexity will be equal to n, which is the number of elements in the array, into log of n. Okay, always keep this in mind. Whenever you have a tree type of subdivision, this is basically a tree data structure. This is how it will look like. You'll have different nodes, but imagine this as a tree, and whenever you have such kind of a logical subdivision and you have independent subarrays which are then again sorted back, and when you have such kind of a complexity, its average case generally works out to be O of n star log n. Okay, logarithmic because you are going performing, or you keep on dividing the array itself, right? That's the reason why you have this logarithmic n coming in, okay? And n is the number of elements in the array. Now the same case will also apply for merge sort, because in merge sort the only difference is going to be that we will not pick up a pivot, but instead we'll just break the array into subarrays in such a way that at the end of the breaking point we'll have all the individual elements as each element in a different array. That's the reason why merge sort will also require more space, because it keeps on creating more and more elements, but that is going to be an explanation on the merge sort, and when we get to that I'll explain you in detail. So that's it for this particular video, and yep, as I already mentioned, you guys know what to do. I'll see you guys in the next one. Bye bye folks.